Now let's look at another example of recursion, and this is a practical one. That is, let's say you have a list of numbers or whatever, names, and it's in sorted order, and this only works if it's in sorted order. One way to do a search for a number in a list of sorted numbers is to jump right into the middle and then check if the thing that you're searching for is bigger than or less than the middle, and then either way you have now thrown away half of the list. It can only be one or the other. So the thing that you're looking for can only be in the top half or the second half, and so that's a very nice way to do search. But of course the limitation is you have to have everything in sorted order first to begin with. Actually sorting is more expensive than searching, so this is only efficient if you have sorted things. Now you can do this recursively. Can you do it iteratively? Yes, actually you can do this iteratively, and it works. And as we said many times before, we're going to solve problems that we can just as well solve using iteration, because we're just learning about how to use recursion. Later on we will see problems where recursion is better, way better than iteration. May not be more efficient, but it's definitely the better way to go. Okay. For binary search, you can do it using iteration. But if you want to write a recursive function, you can see this is one of those nice examples where actually the binary search done recursively is very elegant, and that's one of the advantages. Okay, so let's say you want to search an array of things, check if something that you're searching for is in the list or not, and if it is, where in the list is it? So here's the big assumption about binary search. Whether it's iterative or recursive, you have to assume that the array is sorted. Because what you do is you break the list in half, check if the item is in the first or the second half. Either way, you throw away just half of the list completely with just one check. With one check, you determine if it's in first or the second half. Then you do the same thing with whichever half it's in. If it's in the first half, now that first half you you check if it's in the first quarter or the second quarter, and then with just one comparison you throw away half of that half, and recursively. And here's a very nice way of thinking about how to implement binary search, and this is called pseudocode. Pseudocode looks like code, but it's not really code. It's sort of written in the way most programming languages would be written, or programs in most programming languages would be set up. So for example, an array is described as int a and then some value size. So of course this could just about be valid in C++, not in Java, but pretty close. And so after that, to locate the key value, you check if first is bigger than last. So the idea is you search from array location first to array location last. If first is bigger than last, then there's no way of finding it. So that's like a base case. Otherwise, you find the approximate midpoint between the first and the last. How would you do that? You just take last plus first divided by 2. That would be a good option. You have to be careful because of round off errors. You might run into problems. So you do want to be careful with how you do this, but approximately it's the average of first and last. So then you check if the thing that you're searching for, which is the key, so this is the thing that you're searching for, is exactly equal to the middle. If it is, then you found it, and you return the location, which is the middle value. If it's not equal to whatever's in the middle of the array, then you check if it's less than the mid, which means it's in the first half. So if its key is less than the middle element of the array, you search the first half, that is first through mid minus 1. If it's bigger than, that's the only other possibility actually, that the key is bigger than the middle value of the array, and then you search from the middle plus 1 through the last. Once again, this only works if your array is sorted to start. You can check this recursion against the 3 criteria that we mentioned in the previous video. Make sure you have no infinite recursion. Each call should monotonically increase first or decrease last. Okay, so that first should always increase or stay the same. Last should always decrease or stay the same. Eventually, first will be bigger than last, and you will hit the base case. All right, so make sure you have that base case. If first is bigger than last, there's no elements to search, therefore a key cannot be in that list, and you're done. The other possibility is that the key is exactly in the middle, and you found it. Okay, so you make sure you have the stopping cases. In this case, we do. And then make sure that the recursive calls perform the correct action. That is, if key is less than the middle value, it has to be in the first half. Key is greater than the middle value, the key is in the second half. And this is correct. This would be assuming, of course, that the list or the array is sorted in increasing order, or the way we say it in computer science is non-decreasing order. Either that's more exact, but typically we can think of that as increasing order. Okay, and there's a nice picture of how this works. Here's the middle value of the array. The key is 63. You compare the 63 with the 57. It's bigger than 57, so you can throw away half of the array, this first half, because the key is bigger. So here's the key, it's 63. Middle value is here. So now we throw away the top half. Now we search in this bottom half. Here's the middle value. This first, which is 5, plus 9, which is the last, divided by 2 is 7. So you start at 7. Check if the key that you're looking for is less than this. It is. So then you throw away all of this. And now you're left with 2 elements, and then you very quickly converge to the correct value, 63. It is in the array, and you return that location. So binary search is extremely fast, especially when you compare it with sequential search. So if I could go back, sequential search starts at first, zooms down all the elements, one after another. So there, the worst case is if you're searching for a very large value. You're likely to have to go through all of the elements and then find out either it's there or it's not there. Either the thing that you're searching for is in the list or it's not. That would be the worst case. So you go through every single element pretty much. In comparison, in binary search, every time you compare something, you eliminate half the array. So at the very beginning, with one check, you eliminate half the array, and then you're down to a quarter. With another check, you only have to search through a quarter, and only search through 8 with each additional call. So each time you check, you eliminate half. Okay, and then, so if you have an array of 100 elements, you will never need more than 7 compares. You can work this out. So 100 elements. First step, you cut it down to 50. So that's 1 compare. In the worst case, you do another one, cut it down to 25. Another one, you cut it down, I believe, to 12. That's 3 compares, you got 12. And then next thing you compare, you cut it down to 6, and so on. So once you get to 7 compares, you're done. You have the answer, yes or no. Is it in the list or not? So notice that these binary search algorithm actually solves a more general problem. The original goal was to design a function to search an entire array. Our function allows the search of any interval of an array. So by specifying the bounds first and last, we can search any interval. It doesn't have to be the very first location and very last location. We solve a much general problem, and this is often the case when designing recursive functions. Once we specify how the recursion should work, we realize, well, this can actually say solve a more general problem, starting with any start value in the array and then ending with any ending value. Okay, so that's a quick look at recursion, the way the book does it. Now, we do it very differently in class 2. That is, we use what's called a mechanism-based approach. That is, we look at the stack. We look at how the stack works, and that's very useful for figuring out how recursion works mechanistically, and also to debug stuff. You can, once you realize that it's the stack that can overflow and thereby cause problems, you can understand why runaway recursion can cause a program to crash, things like that. Okay,